Okay, here we go. These are the notes for section 4-1 in your textbook. This is one of the sections we've covered in class. We're going to talk about the idea of a quadratic function and all of its various properties and things that make it unique. So a quadratic function is any function of degree 2. That is, the largest exponent will be 2. Now for those of you that don't remember, when we graph these, they should be a parabola that opens either up or down. Now those can come in two different forms, and we're going to write these in function notation. The first form would be f of x equals ax squared plus bx plus c. This is known as standard form. Keep in mind that f of x could just as easily be y, as those mean the same thing. That is, f of x is taking the place of your dependent variable, y, implying that y is a function of x, f of x. So x is your input, y is your output. X is your independent variable, y is your dependent variable. Right? We've done this before. So your x values would make up your domain. The y values would make up your range. This is not new vocabulary. Now also in here we have a. A value is known as the lead coefficient. We're going to put a lot more emphasis on that term in the second semester. Possible I didn't spell that right, but let's be honest, that doesn't really matter. And the other important value here is c. C is actually the value of the Y-intercept, which will be located at the point 0, c. So it will cross the y-axis at whatever value c is. All right. The other form we're going to see a lot today is the vertex form, which is f of x equals a times the quantity x minus h squared plus k. Again, f of x could still be y, that doesn't matter. And a is still considered to be the lead coefficient. A tells us a lot about our parabola, whether it opens up or down, how it compares to the parent function. All of that, again, will be covered later in the year, except for the up and down part, which we'll talk about here in a minute. Now, the reason this is called vertex form is because these two values, h and k, tell us the location of the vertex. The vertex is located at the point h, k. Now please note that this is minus h plus k, which means when you go to pull these values off to put them in a point, you have to change the sign on h, but you do not have to change the sign on k. It'll be the same as what's in the equation, whereas h you'll have to take the additive inverse, the opposite. So these basically come in two types. Those are the parabolas that open up and parabolas that open down. Now that is easy to tell. We simply look at the lead coefficient. If the parabola opens up, then the lead coefficient is greater than 0. In other words, a is positive. In that case, the vertex, this point right here is the vertex, is the minimum value of the function. In other words, if we look at the parabola and the a value is positive, that tells us that that particular function has a vertex that is a minimum value. We'll get to how to figure out what that value is here in a little bit. Now, if the parabola opens down, then what that tells us is that the lead coefficient is less than 0, negative. If a is negative, then not only do we know that the parabola opens down, it also tells us that the vertex is the maximum value of that function. Again, the vertex being this point, this maximum or minimum point on the parabola. All right, this slide, there's a lot going on here, so bear with me as we go through all of this. Now here in the middle we have an example parabola, and we're going to use it to discuss the parts of a quadratic graph. Okay? Again, these come in two forms. So we could have this be f of x equals ax squared plus bx plus c, which would be in standard form. Now if it's in standard form, the c value tells us the Y-intercept. The Y-intercept is located at the point 0, C. In addition, we can find what is called the axis of symmetry. See, every parabola, every single one, is symmetric. Okay? There is a line of symmetry that runs right through the vertex of that graph, and the left and right sides of that graph, based on that line, are actually identical. They're just mirror images, so there's symmetry. If you look, all of these points, there's one right across from it where it's symmetric. Okay? And actually, now that I look at it, I think my graph is off by a little bit, so let's try to fix that problem. Because it looks to me like the Y-intercept should actually be located right here. That must have happened when I erased it earlier to reset the notes, so let's fix that problem. There we go. So the Y-intercept is located right there at the point 0, 5. Now, as for the axis of symmetry, this line, the axis of symmetry, has an equation based on A, B, and C. That equation is x is negative b over 2a. If we plug in the a and b values from the actual equation, a and b, we change the sign on b, so the opposite of b over twice the lead coefficient. That is the axis of symmetry. It's worth noting that that is also the x-coordinate of the vertex, because the vertex always lies on the axis of symmetry. See? The only point on the parabola that is also on the axis of symmetry. Now, if we want to find the y-coordinate, because that's the x-coordinate, if we want to find the y-coordinate of the vertex, what we need to do is take that value, negative b over 2a, and plug it into f of x to find y, to find f of x. Now we can do a lot of that same stuff out of vertex form. Remember that vertex form is f of x equals a times x minus h quantity squared plus k. And again, we can get the equation of the location of the vertex directly from that equation because it's hk. Remember, we have to change the sign, okay? The sign of h is opposite the sign given in the equation. The y-intercept we can find as well. The y-intercept is when x equals 0. So if we take x equals 0 and we plug that into the function to find f of 0, that would be the y-intercept. Okay, final thing here, and that's not really written, so we're going to write it in down here. The axis of symmetry, when it's in vertex form, is the line x equals h. So whatever h is, x equals h would be the axis of symmetry. Now the last thing that's important from a graph are what are known as the roots. There's two of them. The roots of this quadratic equation. Now roots, we should know from algebra, actually have several different names. Roots are also known as the solutions, the zeros, and the X-intercepts. All of those phrases mean the same thing. So what we do to find those roots is we plug 0 in for f of x. We set the equation equal to 0. So put a 0 here or here, and we solve for x. Now we're not going to do that right now. That's really more for lesson 4-3, which is already posted. So you can go check that video out if you want to see how to start working through that process. Okay, so the types of questions we're going to see in this lesson involve finding various pieces of that information from the previous slide. So for instance, let's say we're asked to find the vertex and we're given an equation in standard form. The way that we find the vertex out of standard form involves basically a couple-step process. The first step is to find the axis of symmetry, which requires us to identify the a value, which was 2, the b value, which is 4, and we don't really need it, but just for the heck of it, we'll go ahead and state that the c value is -6. Now the reason we're not going to need it is because we need to start by finding the x-coordinate. And the x-coordinate is the axis of symmetry. So we're going to find the value negative b over 2 times a. In this case, in this problem, that would be negative 4 divided by 2 times 2, which would be negative 4 divided by positive 4, or an x value of negative 1. As for the y value, well, we simply plug in that x value, negative 1, to the original equation for every x, and we evaluate. So that would be 2 minus 4 minus 6, which would be negative 8. So my vertex is located at the point negative 1, negative 8. The one right below it, letter C, is the same format. Again, when we did this in class, we did examples A and B together, and then I had you try C and D. So instead, for the video, I'm going to go ahead and do C next, because it's the same process as the one above it. And that way we can sort of clump those examples together. So in letter C, the A value is negative 3, the B value is negative 12, and even though we don't need it, the C value would be 10. We would start by finding the axis of symmetry, which is negative b over 2 times a. That would be 12 over 2 times negative 3, or 12 divided by negative 6, which would be negative 2. That's our x value. For y, we take that x value of negative 2 and we plug it in for the x's in the equation. So negative 3 times negative 2 squared minus 12 times negative 2 plus 10. That would be, and I'm going to show a little bit more work on this one because the lead coefficient is a negative number. So we'd square negative 2. 12 times negative 2 is positive 24 plus 10. So we're looking at negative 12 plus 24 plus 10. Well, that would mean that y equals 12 plus 10, or 22. So our vertex would be located at the point negative 2, 22. Okay, that brings us to the other form, which is vertex form. Now, in my opinion, finding the vertex out of vertex form is easier, which is not shocking. There's a reason it's called vertex form. So all we have to do to find the vertex is located at the point hk. And if we remember, this equation is in that form, a times x minus h squared plus k. So if we look at that, that tells us that the h value is 2. Remember, we have to change the sign on h. So since it's negative in the equation, h is really positive 2. And k is exactly what it says in the equation. K is 5. So this vertex is located at 2, 5. Same thing in the next problem. Here we have an h value of negative 7 and a k value of negative 2. Notice how I ignore this number in front of the parentheses. It doesn't matter for finding the vertex. Whatever it is unimportant. All that matters is what number is here, as its opposite is h, so h is negative 7, and what number is here, because that number will be k. So my vertex on letter D is negative 7, negative 2. The next thing will be a multi-part question involved around the axis of symmetry. But this is essentially asking us to do the same thing that we just did. Because by asking us to find the axis of symmetry and then asking us to find that maximum or minimum value, that is the same work. That's finding the vertex. So, for part A, to find the axis of symmetry, we start off by identifying A, B, and C when it's in standard form. So A is negative 1, B is positive 2, and even though we don't really need it, C is negative 1. Then we say the axis of symmetry is negative B over 2A. And we plug in the exact same numbers just like we did on the previous slide. That would be negative 2 divided by negative 2, or positive 1. So the axis of symmetry is the line x equals 1. Now if you just write 1, that is not an equation of a line, so it is incorrect. Your equation of a line has to be either in slope-intercept form, which would be y equals mx plus b, or it needs to be x equals a number, which would be a vertical line. In this case, the axis of symmetry is always a vertical line, so it should always be x equals a number, and that number should be given by negative b over 2a. Now, for part b, whether it is a maximum or a minimum depends entirely on the a value. In this case, a is negative. We discussed on an earlier slide that if a is negative, that tells us that this particular parabola opens down. And if the parabola opens down, that means our vertex is the top point, the highest point in that shape, which would be a maximum value. And finally, for part C, we need to take our value from part A and plug it in for x. So that would be negative 1 squared plus 2 times 1 minus 1, or negative 1, pen is starting to mess up a little bit, plus 2 minus 1, which would be 0. So that value would be y equals 0. There are 3 answers for this type of question. And in this case, the vertex would be located at 1, 0, telling us that the axis of symmetry is x equals 1, that it's a maximum value because the a is negative, and that the y-coordinate of the vertex, the maximum value, is y equals 0. Vertex form is not that complex, actually. All we really need to be able to do to answer all 3 parts of this question is identify that a is 2, that h is negative 3, and that k is negative 5. Because if it is in vertex form, the axis of symmetry is the line x equals h. So in this case, that would be x equals negative 3. B is still based on the a value. In this case, a is positive, which means that this graph opens up, and it means that the vertex is the lowest value, which would be a minimum. Finally, for letter C, well, it's not nearly as intense as the other version because that value is y equals k. So in this case, that would be negative 5. Moving on. Okay, so finding the y-intercept. This is probably the one place where it is more useful to be in standard form than in vertex form. So if we're looking at the graph in standard form, the y-intercept is at the point 0, c. Well, c is negative 5. So that answer would be 0, negative 5. Same for the problem directly below it. C is 4. So the y-intercept is the point 0, 4. Now, a lot of people made the mistake of thinking, oh, well, that means that whatever that value is sticking off the end of the equation, that's always going to be my y-intercept. And that's only true for when it's in standard form. When it's in vertex form, that is not the case. This is a k value. It's not the y-intercept. For vertex form, to find the y-intercept, what you have to do is plug in a 0 for x and evaluate. So that would be negative 2 squared plus 3, or 4 plus 3, which is 7, which means my y-intercept is the point 0, 7. Notice how 7 is not the number sticking off the end of the equation. There's no avoiding this little bit of work. So on letter J, we're going to plug in a 0 for x, and we're going to evaluate. That would be negative 2 times 1 squared minus 4, which would be negative 2 minus 4, or negative 6. So the y-intercept is the point 0, negative 6. Okay, that brings us to graphing, and it's not just graphing, it's also identifying all of the information that we've already done along the way before we graph it. Now, all four of these examples we are going to graph by hand. But remember that the table function on your calculator is more than capable of graphing these for you. I don't want you to be dependent on the table function, and I don't want you to be dependent on a graphing calculator. What you should be able to do is generate the table by hand, and then once you can generate it by hand, you can allow the calculator to generate the table for you. If you have questions on how to use the table function on your calculator, you need to see Mr. Wills, because he is not going to be putting that in this video. Okay, so the first question here asks whether this particular function is opening up or down. Now hopefully by now we've established what that is. We need to look at these A values. A is 1 because there's no number listed. B value, which is -6. And eventually we're going to need the C value. C is 8. As soon as we see the equation, we should, at least in our head, immediately identify A, B, and C. Now as for whether this opens up or down, this particular function opens up. How do we know that? We know that because A is positive. And when A is positive, the graph opens up. Now, we're not going to do these in order because the vertex is sort of a combination of these next two steps here. So we're going to start with the axis of symmetry, -b over 2 times A. So that would be 6, +6, because the opposite of -6, over 2 times 1, which would be 3. So the axis of symmetry is x equals 3. Now, we already know that this graph opens up. If it opens up, then we are looking at a minimum value. So we should circle minimum. But then in this blank, it doesn't want us to write max or min. What it wants us to do is figure out that value. So again, to do that, what we do is we take the equation and we plug 3, because that was the axis of symmetry, in for x. And we evaluate. That would be 9 minus 18 plus 8. That's -9 plus 8, or -1. So that value would be y equals -1. Now notice we have an x value and a y value. Those make up your vertex. So your vertex is located at the point 3, -1. Okay? Whatever your x value is for the axis of symmetry, I don't really want to use a blue highlighter there. That's no good. Let's try green. Whatever your x value is the x coordinate of your vertex. Whatever this max or min value is, that's the y coordinate. Finally, we have the y-intercept. Remember that that is the point 0, C. And from up above, C is 8. So that would be the point 0, 8. Now, once all of this is filled out, we should go down and graph this using a t-table. Now, I'm actually going to do more than a t-table because I want to show a little bit more work than that. So we're going to put x in the left column, then we're going to show our work, and that will result in a y. Now, your table needs to have a minimum of 5 points. So we're going to do 5 rows in our table. Perfect. This middle row, the third row, is where we're going to place our axis of symmetry, which from our work was x equals 3. We already know the end result of that, because it's the vertex, is that y will be -1, meaning that 1 point from our graph will be the vertex, the point 3, -1. Now, the beauty of parabolas is that they are symmetric. So if we put the axis of symmetry in the middle of our table, it cuts the amount of work that we have to do in half. So we should pick 2 points on each side of 3. 2 numbers less than 3 could be 2 and 1. 2 numbers greater than 3 could be 4 and 5. Now what we do is we take this x value and we plug it into the equation. So that would be 1 squared minus 6 times 1 plus 8. and we feed this to our calculator. That would be 1 minus 6 would be negative 5, plus 8 would be positive 3. So 1, 3 is a point on the graph. Same for 2. 2 squared minus 6 times 2 plus 8. That is 4 minus 12 plus 8, which would be 0. So the point 2, 0 is on our graph. Now, believe it or not, that is all the work that we have to do, because as I mentioned, it's symmetric. So if this distance is 1 and this distance is 1, then the x values will be the same. So this x value has to be 0, meaning the point 4, 0 is on my parabola. The same can be said between 3 and 1 is a 2-unit difference. Between 3 and 5 is a 2-unit difference. So if 1 has a y value of 3, so does 5. So now we have our 5 points that we can graph to get the picture of this particular parabola. So we have the points 1, 3 from here, 2, 0, 3, negative 1, 4, 0, and 5, 3. Now, in addition to that, we also know the y-intercept is 0, 8, so we might as well graph that point. And if 0, 8 is a point, so is 6, 8. Because again, there's that line of symmetry. That point's 3 units to the left, so there has to be a point 3 units to the right. Now, we're going to draw our curve through those points. And there's the graph of our parabola. Let's do another one. Okay, same deal. We need to identify that A is negative 2, that B is positive 4, and that C is positive 1. I almost wrote negative 1, and as you can see, I already fixed that, so no judgment. Okay, does this open up or down? Well, A is negative. That should tell us that it opens down. Next, we're going to do the axis of symmetry, negative b over 2 times a. That'd be negative 4 over 2 times negative 2, which would be negative 4 divided by negative 4, or x equals 1. Then we're going to plug that value in. Now, since it opens down, that means the vertex is a maximum value. So we're going to plug in 1 for x, which would be negative 2 times 1 squared, plus 4 times 1 plus 1. That would be negative 2 plus 4 plus 1, or 3. So that maximum value is y equals 3. And my vertex is the point 1, 3. As for the y-intercept, that is the point 0, c, and c is equal to 1. So that is 0, 1. So now we're going to do a table. Again, we're going to plug in some x's. We're going to do a little bit of work that'll spit out a y, and we'll turn those into points to graph on the graph. So again, we need 5 rows in this table. That middle row has to be our axis of symmetry, which is x equals 1. We already know that that results in the vertex, and we already know that the vertex has the coordinates 1, 3. So that row is already done. We've already done that work. Now here's the beauty. The two numbers below that would be 0 and negative 1. The two numbers above that would be 2 and 3. We already know the y value for the y-intercept, which is when x equals 0, is 1. So this time we actually have to do significantly less work, because once we apply our symmetry, we already know 3 of the 5 points we need to graph. With negative 1, we have to plug that in. So negative 2 times negative 1 squared plus 4 times negative 1 plus 1. That would be negative 2 minus 4, which is negative 6, plus 1 is negative 5. So the point negative 1, negative 5 would be on my parabola, as would the point 3, negative 5. Because again, symmetry. Okay, we've got symmetry in these numbers. So we go in and we graph these 5 points. Negative 1, negative 5. 0, 1. That's up 1 from the origin. 1, 3. 2, 1. And 3, negative 5. That would be the 5 points we need to draw our curve and finish this problem. That is 2 good examples of graphing out of standard form. So now let's look at vertex form. Okay, so vertex form, the side work and the graph itself both go a little bit quicker. And I'm actually going to show you a shortcut for graphing once we get to that point. So the first thing we need to do is identify that A is equal to 1, because there's no number in front of the parentheses, that H is negative 2, and that K is negative 1. Now, as for the opens up and down, that is still based on A. A is positive, which means that this particular graph is opening up. And that also tells us that our vertex is a minimum value. The axis of symmetry for vertex form is x equals h. So that would be x equals negative 2. The actual value is y equals k, which would be negative 1. And that means our vertex is at the point negative 2, negative 1. The y-intercept is the hard part. It is when x equals 0. So we have to plug that into the actual equation. Y equals 0 plus 2 quantity squared minus 1, which would be 3. Because this would be 2 squared, which is 4, minus 1 is 3. So the y-intercept is the point 0, 3. Okay, so now I'm going to show you a shortcut for graphing, and there's actually a pattern to the XY table when you graph a parabola. So what we do is we graph the vertex, which is the point negative 2, negative 1. And then if we notice, when A is 1, we had an example of that on a previous page. Let's go back and take a look at it real quick. We went out 1, up 1, out 1, up 3, out 1, up 5. So my run was 1, and my rise followed a pattern there. I went up by 1, up by 3, up by 5. The next one would have been up 7, but that's up the top of the graph. If you notice, the same pattern exists here in the y values. We have the vertex, we add 1, and then we add 3 to that value. So plus 1, plus 3, the next one would be plus 5. Plus 1, plus 3, plus 5, plus 7. Okay? So, if we go back here and look at this graph that we're trying to graph, here we go. We are going to go out 1 to the right and up 1, out 1 to the left and up 1. Those 2 points appear on the graph. If we then go from those points out 1 and up 3, that would be the next set of points on the graph. If we go from those, we go out 1 and up 5, that would be the next points on the graph. Now the ones after that would be up 7, which would be at 15 and are off the top of the graph. So there's our graph for our vertex form. Again, we can also use the table function on our calculator to graph this. We simply need to start our table 2 less than the axis of symmetry, which would be at x equals negative 4. Let's do one more example graphing out of vertex form. So here we have A is negative 2, H is positive 3, and K is positive 8. Since A is negative, That means, the same as it has on the previous three examples, that this particular graph opens down, which makes the vertex a maximum value. So we can answer those two questions right away. The axis of symmetry in vertex form is x equals h. H is 3, so that would be the line x equals 3. The actual value of the vertex is the point y, or is the value y equals k, or in this case y equals 8. This means the vertex is located at 3, 8. As for the y-intercept, again, that is when x equals 0. So we evaluate that function when x equals 0. We plug a 0 in for x. That would be negative 2 times negative 3 squared plus 8, which would be negative 18 plus 8, or negative 10. So the y-intercept is the point 0, negative 10. So let's go to the graph. We're going to start at 3, 8. Now this one is a little bit different. On the previous example, a was equal to 1. So our pattern went out 1, up 1, out 1, up 3, out 1, up 5. However, this one has an a value of negative 2. So when we go out 1, we're going to go down 1 times negative 2, or negative 2. Then we're going to go out 1 and down 3 times negative 2, which would be negative 6. Then we're going to go out 1 and go down negative 2 times 5, which would be down 10. Notice we've passed through that 0, negative 10. That was the y-intercept. So there's the graph of that parabola. I didn't do a great job there, but that's okay. All right, next up, here's a real-world question based on this skill. So we're going to go through this. Emma threw a softball to second base. The path of the ball can be modeled by y equals negative x squared plus 8x plus 2, where y represents the height in feet of the ball x seconds after it is, and we just stated, thrown in the air. So we'll simply change that word. A asks us to make a sketch of the path of the ball. Include and label the following: both axes, the y-intercept and the vertex. Okay, so this means we need to graph that equation. And to do that, we really need to know the axis of symmetry. So we start with negative b over 2 times a. Now if we look at this equation, from that equation right there, a is negative 1, b is 8, and c is 2. So we would go negative 8 over 2 times negative 1, which would be negative 8 over negative 2, or positive 4. Then we would plug that value in to figure out the y value that's associated with. So negative 4 squared plus 8 times 4 plus 2, which would be negative 16 plus 32 is 16 plus 2 is 18. So the point 418 is the vertex. So 418 is the first point that we graph. Now notice the a value is negative 1. So from there we're going to go out 1, down 1. From there we're going to go out 1, down 3, because our a value is a 1. Out 1, down 5 would put us right there, right there. Out 1, down 6. Something is off here. What did I mess up? 418. It might be this, probably right in here somewhere. Negative 16 plus 32. Yeah, that would be 18. Out 1, down 1, out 1, down 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, that's what I'm doing wrong. I'm only going down 6 in my head. Okay, so we need to go out 1 and down 7. Again, we're going down 1, down 3, down 5, down 7. That's the pattern. Okay? So, we're going to then sketch that graph by going through those points. Now it says to label some things here, so let's label some things. We have a Y-intercept right there. This is the Y-axis, which is already labeled, so I'm not really sure why they want us to label that. Here's the X-axis. It is already labeled. And the vertex, which would be this point right here. Okay, question part B says, at what height was the ball thrown? Justify your answer. Well, the problem says that Emma threw the softball, which means Emma is throwing the ball when time is equal to 0. So when x equals 0, that's saying, what is y when x equals 0? That's what that question is really asking us. So at time 0, we're at the y-intercept, which is the point 0, 2. So we would answer with Emma threw the ball with an initial height of 2 feet. And that would justify our answer because we said the words initial height, which is how we know that's where the ball was thrown. That's our precise language we're searching for on this type of problem. Now I may need to flip back and forth because this problem continues on the next slide. What is the maximum height of the ball? When does it reach this height? Explain your reasoning. I mean, just look at the graph. At what point does the maximum height occur? It occurs at the vertex. The vertex, we've already stated, is at the point 418. So the answer to this, all parts of this, are located at the vertex, 418. So we would say the maximum height is 18 feet. This occurs at 4 seconds. And it says, explain your reasoning. We would say the vertex is 418. And that should explain everything we need because the maximum value has to occur at the vertex. Okay, letter D. How high was the ball 6 seconds after it was thrown? Justify your answer algebraically. Well, that means we're going to plug in 6 for x. So let's see. That would be y equals, and I need to go back and look because I don't have the equation memorized. Negative 6 squared plus 8 times 6 plus 2. That'd be negative 36 plus 48 plus 2. That would be 12 plus 2, or 14 feet. We've shown our work. That justifies algebraically. Okay, and finally, was the ball going up or coming down 6 seconds after it was hit? Well, everything, and I completely misspelled that word, so let me just start over there. After we go past the vertex, after t equals 4, I should say x. After x equals 4, the function is decreasing. That is our explanation for stating that after 6 seconds, the ball is coming down. We have explained right there in that first sentence that we understand that the function is increasing from 0 to 4 seconds, which is the vertex. Once it gets to 4 seconds, it stops moving up and starts moving down. And anything above 4 seconds, 5 seconds, 6 seconds until it hits the ground would be coming down. Okay, the final thing is to discuss how to use the graph of an equation to find the roots, solutions, zeros, x-intercepts. Notice how many different words I said there, because roots, solutions, zeros, and x-intercepts are all exactly the same thing. So you're going to see these problems where they give you a graph and they say find the solutions and the factors of each quadratic. So let's talk about the relationship between those two. The solutions are the x-intercepts. So where does this graph cross the x-axis? It crosses it at x equals 0 and x equals -2. So that's how we would write our solutions. We would simply write the x-intercepts. Now the factors, that's a little bit more complicated because the factors are what the equation would look like if we factored it before we solved it and found the solutions. So the general way that we write those is we write x minus whatever the solution is. 0 is a really unfortunate number to have in the first example because it's a special case. Because I don't need to write x minus 0 because x minus 0 is x. Over here I would do x minus -2, which would really be x plus 2. So my factors are x and x plus 2. Let's do another one. This crosses the x-axis at x equals 6 and x equals 8. Those are the solutions. The factors would be x minus 6 and x minus 8. The opposites. Okay, here's another one. Where does it cross the x-axis? The only point where it touches the x-axis is the point x equals 1. Now we discussed in class, and we will discuss a lot further later in Algebra 2, how this is called a double root, and that in reality there are two factors, both of which would result in an answer of x equals 1 if we set them equal to 0. So they would both be x minus 1. Finally, on letter D, the solutions, well, it doesn't touch the x-axis. And if it doesn't cross the x-axis, then it has no real solution. Notice I didn't write no solution. I wrote no real solution because that quadratic still has two solutions. They're just complex numbers. So we will come back to that later in the year to discuss it. And the factors, we would then say that it would have no real factors as well. Because the factors of that function would be imaginary. They'd be numbers involving I, the square root of -1. I am fairly certain that is the last slide. It is. So that completes our section 4-1 notes.